turn on the projector and get the PowerPoint up from current slide. All right, let's go over a couple of the announcements. We are at midterm, okay? In fact, we're just into the second half of the fall term. And what does that mean? Wednesday, I'll need to enter midterm progress reports. And right now, folks, I have two scores for this class for the first half term. I don't have any research papers in, and I have 2 first tests in. So please get me at least one of those 2 objects, or both, by Wednesday. Otherwise, I have to put down that you have an F at midterm. Not that it means anything, except you might start getting bugged by people that, you know, do you need tutoring, do you need help? And if you do, I mean, by all means, take advantage of it. But if it's not an issue of that you need help, it's just an issue you haven't turned something in, please get it in today or tomorrow. I have to do the reports by Wednesday. For those of you who are interested, Miss Lawson's state coronation is coming up this Thursday. I'll go over the rest of that later. Okay. Our volleyball team will be playing Southern Union Community College down in Wadley, Alabama. I don't think I've ever been there. 6 p.m. tomorrow, okay? They'll be leaving here around 2 p.m. to get down there. So if you happen to be driving by Wadley tomorrow evening around 6, stop in and cheer the team to victory. And that's over with. And we are rapidly approaching the deadline for the NASA's Community College Aerospace Scholars Program. The deadline is Wednesday, day after tomorrow. So I've got the information here, the website's here. If you're interested, please get your applications in. How big a process is the application, Fred? Do you remember? Is it?
I don't think it's necessarily short, but I don't think it's too long.
Okay. All right. So please, if you better get working on it if you plan to have it in by Wednesday. Any questions on anything we've done so far? Finally, we'll get started today then. We're doing example 6, which is on, it's chapter 8, integration techniques and improper integrals, mostly integration techniques. 8.3 is trigonometric integrals, and we're on page 536, example 6, sort of the bottom half of the page. So let's get my pen set up, and let's do the integral, definite integral from 0 to pi fourths of tangent fourth x dx. All right. Now, good deal. Here's Josh. You got another second mini-term PE or? Oh, no. Okay. All right. Now, where would you begin on something like this? Do you remember our protocol, you might say, that we did on, they called it guidelines. Okay? The first was when the power of secant is even. This doesn't have any secants. When the number 2 was when the power of tangent was odd. This one's even. And number 3, when there are no secant factors, hey, that's this one, and the power of tangent is even and positive, yes it is, it both counts, then what do we do? Any ideas?
Convert to secant.
All right, so what we're going to do is break this down into 0 to pi fourths, that stays the same. And we'll do 1 tangent squared x, and the other tangent squared x will be, what did you say it was?
Secant squared x.
Secant squared x minus 1. Okay, remember those identities there because they don't always, it's not always the same order with the numbers and the signs and stuff like this. So be sure you get that right. And then dx. All right. Does that help us any? How does that help us? Or if you go back to your guidelines, when the power of secant is even and positive, that's number 1. Okay? So what we have now are 2 integrals. So let's do the first one. Integral from 0 to pi fourths. And the first factor there, or integrand there, will be tangent squared x secant squared x dx minus the integral from 0 to pi fourths tangent squared x dx. Do you see that? Okay? What we've done is multiply this through and then split that as 2 integrals. Here's the first one and there's the second one. Got it? Make sense? Okay, what do we do with that one then? Okay. What else is secant squared x that may be of interest here? Isn't that the derivative of tangent x? Recall? Yes, that's why we wanted a secant squared there, because that is the derivative of tangent, and here we have a u du, right? In fact, it's a u squared du, right? So maybe a u substitution would be in order here. What would that be? I just gave it away. Not tangent squared, but tangent x, then du is equal to, really? Secant squared x, right? Okay, let's go back and check our identities here. Front and side cover of the book, derivative of tangent x is secant squared, or they have tangent u, secant squared u du. So that's secant squared x dx. So this is our du, and what would that be? If u is tangent x, what would tangent squared x be? U squared du. But we've changed variables. So on this line here, when tangent is equal to 0, when tangent of 0, what's that equal to? When x equals 0, tangent x is equal to, what's tangent of 0? I've got to talk with your trig teacher. 0, excellent. And when x is equal to pi fourths, that makes tangent of pi fourths, u would be 1. Excellent. Okay. I think I could probably even do that integral now. Let's see what else we have here. Minus a tangent squared x. Now, how in the world are we going to do that? Go back to our protocols again, or guidelines. Power of secant is even. We don't even have a secant in that one. Power of tangent is odd. Nope, it's even. But what's the third one? When there are no secant factors. Same thing we used before, right? And the power of tangent is even and positive. It is. Convert the tangent squared to to what? Same as we did before. Secant squared x. Can I split this up? Dx minus, and that's minus a minus, so that's a plus, integral from 0 to pi fourths dx. Secant squared x minus 1, so we'll do the secant squared x dx, and then a 1 dx, which is just dx. What's the antiderivative of secant squared x? Haven't we just done it? That's tangent x. So this would be a minus tangent x evaluated from 0 to pi fourths. I can't write, okay? Plus, what's the antiderivative of dx? X evaluated from 0 to pi fourths. And this would be, what's the antiderivative of u squared? U cubed over 3 evaluated from 0 to 1. So what does that give us? The first one? When you, second? 1/3 minus 0. I'll take care of that one. Minus, and what's tangent of pi fourths? 1 minus 0. I'll take care of that one. Plus, and what's this one? Pi fourths minus 0. Okay. So that gives us pi fourths minus 2/3. Right? Now, pi fourths is something around 3/4, right? A little bit more than 3/4. And 2/3 is 2/3. So that's going to give us something probably a little bit greater than 1/6. Okay? And sure enough, it's 0.119. I believe 1/6 is 0.1. Less than that, it says. Well, they say 0.119. I don't know if that's what you got or not. Is that what you got? Okay. Oh, I think it was 1/12, wasn't it? If that was 3/4, that would be 9/12 minus 8/12. Yeah, it's 1/12. And 1/12 is, I don't remember, 0.0 something another. And this is a little bit more than that, 0.119. That seems reasonable. All right. Now, they have another little statement at the bottom of that one. The area represented by the definite integral shown here, try using the midpoint rule to approximate the integral with n equal 15. Yes, I'd love to do that. What a pain that sounds like that would be. You should obtain an approximation that is within 0.1001 of the actual value. I would say if you had a programmable calculator that you wanted to try that, I might do it that way. But you see, the area under there is quite small. You see the graph of it there. And it hangs really close to 0 up until you get close to pi/8, and then goes up, but it still only goes to 1 there. So that's a very small area. It looks pretty big there, but when you look at the numbers, on the horizontal scale, you're just barely up to 3/4, and on the vertical scale, you're very narrowly going to 1. And so, yeah, you don't have much area under there at all. So I'll buy that. Now, they have another blurb at the top of page 537 that says, for integrals involving powers of cotangents and cosecants, you can follow a strategy similar to that used for powers of tangents and secants. Also, when integrating trigonometric functions, remember that it sometimes helps, to convert the entire integrand to powers of sines and cosines. They sort of use that as when all else fails, I kind of look for that early on. If I don't see anything that looks pretty obvious to do, I go for that. So let's do example 7. Any questions on 6 before we leave it? Does it make sense? Any questions? All right. Let me erase. And let's do example 7. Find this. The integral of secant x over tangent squared x dx. Now, what would be your first inclination on a problem like that? And feel free to blurt anything out. A lot of times you're going to try several things before you find something that works. What would be your first inclination here?
Is it a log function?
Okay. Log of a tangent or something like that. I don't see anything. Say again? Do something about tangent squared. What were you? Yeah. Okay. That would be my first inclination. Look for the most complicated part of the problem, and that would be the denominator. And the simplest part of that would be a tangent. And then I would look at that and say, can I do anything for u substitution there? Well, that would be okay. Let u equal tangent x. If that numerator had been a secant squared, that's the way to go, folks, because if the u was tangent x, du would be secant squared x. But it's not a secant squared, it's a secant. So that route sort of gets squished pretty quickly because you don't have a secant squared in the numerator. All right? The second thing I would think of, tangent squared is related to... Okay, yeah, it is, and that's where we're heading. But the next thing I thought of was Pythagorean theorem of Pythagorean identity, that tangent squared is, just like we just did, secant squared minus 1, right? But that puts your denominator with the binomial in it, and that's usually not a good thing. If the binomial is in the numerator, yeah, you can split it up and go to town with that. But with the denominator, you can't. So there's another dead end. So now, who said it? Okay, let's try sines and cosines. All right, let's see what that leads us to. The integral of, what is secant? 1 over cosine x, and what's tangent? Okay, but it's in the denominator, so that would be a sine squared x down here and a cosine squared x up there. Agree or disagree? What you think? Did I do it right? Don't say yes just because I'm the instructor. What do you think? Did I do it right? Tangent squared is in the denominator, so that puts sine squared over cosine squared in the denominator, which then you can flip it and make it cosine squared over sine squared. Right? All right. Now, what can you do with that? Yeah, cosine will go into that one time. Okay, one cosine. Okay. Cosine and cosine squared goes cosine times. Now, anything look like it might work here? Anybody? Let u equal what? Sine x. I like it. Then, next step, du is equal to what? cosine x dx. Hey, 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 what do we have there? We have the integral of cosine x dx is du over, and sine squared x would be u squared, which I don't like. How would I rather write that? U to the minus 2 du. Ha! I like that better. What would that give me? U to the minus 1, a negative. Okay. Plus c. But what is u, or what are you? What are you?
Sine x.
Sine x. So this would be a minus 1 over sine x plus c. But what's a 1 over sine x? Cosecant. Can't write. I think it's minus cosecant x plus c. Ho! That's what they got to. Good for them. All right. Any questions on that? Okay. So, don't feel like you're not getting it if you try something and it doesn't work. That's part of it, you know. Keep trying things. Well, okay, that didn't work. What else could I do? What else could I do? What else could I do? And keep doing until you until you enlighten yourself into what might work. Make sense? Okay. Let's see if we can get the bottom half of 537 to show up on the screen somewhere here. Integrals involving sine cosine products. Now, I think for those of you who did take pre-calculus trig under me, you probably remember me saying, you're not going to use these very often, so I wouldn't worry with them. Just know how to look them up and use them. Here's where we'll use them, okay? I'm not a memorizer, so I don't waste a lot of time and effort trying to memorize things, especially things that come along so few and far between, I'm not going to remember them anyway. So, integrals involving the products of sines and cosines of two angles occur in many applications. Okay, we'll take your word for it. Actually, they do. In such instances, you can use the following product of sum formulas. So basically, write them down, know where to look them up, use them as you need them. So here's the first of these. Sine mx sine nx is 1/2 of cosine m minus nx minus a cosine of m plus nx. You might see a reason why I don't try to memorize this. So many places to make a sign error. Is it a minus here and here, but a plus there? There's so many different combinations you can do of your signs. Look them up. I don't want you trying to memorize. Okay, now, another thing to note here, the grouping symbols. The m minus n in parentheses here, the bracket here, but this one and that one are your outside. So this 1/2 goes with both of them. I would be really tempted to put this over 2 and that over 2, just so I wouldn't think it's only that first one. Because there's so many grouping symbols there, you might think it's just this one. It's not. It's both of them. Okay. Now, sine mx cosine nx is 1/2 of this entire thing here. This is the sine gives you cosine cosine. Sine cosine gives you sine sine. Duh! Okay, this isn't making lots of sense. And you've still got the m minus here, but then a plus here, and then a plus there. And if it's cosine cosine, it's 1/2 of everything, and it's back to cosine cosine here. So there's no really good pattern here. The cosine cosine has the minus here, plus there, plus there. Okay. Only thing that's consistent here is always your m plus n is the last term. And here it didn't have to be the last term, they just did it so it would look like the other. You know, minus n in front, of course here it did. In fact, both of these could have been switched with no loss of generality. But not worth trying to memorize. The patterns are murky enough, I don't even find them being patterns. So look them up when you need them. Now, it might seem like the thing you're missing is cosine mx sine nx. That's the same as this, okay? So just switch them around and you got it. There's no reason muddying the water with that. Okay. So use them where you need them. All right. That leads to example 8. Find the integral of sine 5x cosine 4x dx. Now, when I said you will find use for these, if any of you continue in math far enough to take Fourier analysis, this is a very typical Fourier problem, okay? And I'm trying to think which branches of engineering use that. It seems like it might be electrical, but I may be wrong on that. Any of you pre-electrical engineering? Possibly, okay. So I can't remember. That doesn't ring too true to me. I can't think what in electricity they do, but for some reason it is. It may be some other form of engineering, or it may be very few and far between. It may be a purely math thing, so that might be in your plate, okay. But Fourier analysis is a powerful tool, and it does use products of signs. But if you're doing that course, you're going to use them often enough, you'll know where to look and find them, or you'll remember them one. So, which one of these three is this addressing? First, second, or third? From the gray box. The second one. And that says this is equal to, you can pull the 1/2 out from the radical, okay, put your integral sign, and then write down what's inside. Sine of what? Sine x. Because your m here was 5, your n here was 4, 5 minus 4 is 1. So that's just sine x plus sine of 9x dx. Okay? Now, the question I have, do you want to handle this with one integral or you want to split it into two? I really don't care that much. Which would you rather do? One integral or two? Give me a preference. Say again? Two. Huh?
We can just do it as one.
Just do it as one, is what you said? Okay. What's the first? That's 1/2. Antiderivative of sine x is? Negative cosine x. Antiderivative of sine of 9x would be? Negative cosine of 9x divided by 9. I like to do that, but they probably don't in the book. And then what else would you have? Plus c. Okay? So this would be 1/2 or minus 1/2 cosine x minus 1/18 cosine 9x plus c. Minus, they put it over 2, minus cosine x over 2 minus cosine 9x over 18 plus c. Done. All right. They're easy to look up and easy to use once they're looked up. I just don't count it worthwhile trying to memorize that. If you're a great memorizer and it's fun for you to do and a challenge and all that kind of stuff, knock yourself out, you know. Have fun with them. All right, to erase. See how the book did them. Considering the second product of sum formula is one y'all found, we'll rewrite this as exactly what we did. Sine of 5x cosine 4x dx is 1/2. That goes on the outside. The sine x plus sine 9x dx on the inside. And they integrated just one time using that. And the antiderivative of sine is minus cosine. And the antiderivative, of cosine 9x of sine 9x is minus cosine 9x over 9 plus c, and then they just put the 2 underneath both of those. Minus cosine x over 2 minus cosine 9x over 18 plus c. All right, any questions? Just basically identical steps to what we did. None? All right, that is the last slide in the slide set, and it's also the last example in the text. So we're through with 8.3. Homework exercises here include any of the odds 9 through 13. They're all at Calc Chat. 7's at Calc View. Any of the odds 15 to 19, they're all at Calc Chat. Excuse me. Any of the odds 21, man, I'm having trouble breathing. I got all congested over the week. I guess a change of weather, I don't know. But this is the first time I've been chilly in months. I mean, months. Many months. All right. Any of the odds 21 to 33, they're all at Calc Chat. 27's at Calc View. Either 35 or 37, they're both at Calc Chat. 39 should be at Calc Chat. 41 should be at Calc Chat. Any of the odds 43 to 47, they should all be at Calc Chat. 43 at Calc View. Any of the odds 49 to 57, they should all be at Calc Chat. 59 to 65, they should be at Calc Chat. 61 should be at Calc View. You can explore doing 67 and or 69 if you would like. They should both be at Calc Chat. 71 should be at Calc Chat. 73 should be at Calc Chat. 75 should be at Calc Chat. And 77 should be at Calc Chat. You can do either 79 or 81. They should both be at Calc Chat. 83 or 85 should both be at Calc Chat. And then 87 is should be at Calc Chat. We had some Wallace formula thing back 15 to 19. These, I'm guessing, are a little more advanced, but I'll let you decide that for yourself. And then, guess who I mentioned? Fourier series, okay? And that's number 89. So if you want to get a jump on that, you certainly can. And then there's more on the Wallace product here. John Wallace came up with this in 1655, and then in 2015, physicists Carl Hagen and Tamar Friedman, also a mathematician, stumbled on a connection between quantum mechanics and the Wallace product. Frankly, just about anything to do with quantum mechanics is almost stumbling. You know, it's just really bizarre. But anyway, they did find this, so you might say, what's the point? Here's a point. Okay. Pretty interesting if you want to follow that. And then at the bottom of the page for further information for alternative proof of the Wallace product, there is an article, and they give you the article, the journal, and everything. If you wanted to follow that up and report on that, you certainly could. Any questions? 8.3. So let's move on to 8.4. All right. We will go from current slide. All right. Still in Chapter 8, integration techniques and improper integrals. We're mostly going to be doing integration techniques. And there's that beautiful shot. I'm pretty sure it's a Hubble Space Telescope shot. Far right, that's the one they were talking about, the connection with the Wallace formula. Pretty incredible. Okay? 8.4 is trigonometric substitution. We were doing trigonometric integrals. That's different from trigonometric substitution. Okay? In fact, trigonometric substitution is different from your usual substitution. Okay? In your usual substitution, it's let me get my pen set up. Let u equals something to do with x, right? Some function of x. Then you do a du. Blah, 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 dx. Okay? That's the way we go there and substitute here. When you do a trig substitution, now, I'll give you my preference. The book, I think, pretty much does this too. You have a function here inside an integral, okay? And you say, how does that look like some trig identity? And then you'll do let I like to do tangent theta equal blah, 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 okay? Something to do with x. So you see, in fact, usually it is x or u or something like that. So you see, before, it was a single variable be some function of x. Now it's going to be a function of theta to be x, okay? So you're kind of doing it in reverse. You're going from something complicated and going to something simpler. Here, this is complicated enough, but then we're going to let a trig function be the variable. So rather than a new variable being a function of the old variable, we'll let a trig function be what the old variable is. So in that way, it is a little different. Okay? So our objectives here, use trigonometric substitution to find an integral. Yep, that's what we're doing. And we'll use integrals to model and solve some real-life applications. All right. Now, you can use trig substitutions to find integrals involving radicals that look like this. A squared minus u squared, square root of a squared minus u squared, the square root of a squared plus u squared, and the square root of u squared minus a squared. Now, in these cases, your u is your variable, a's are constants. Okay? U the variable, a's constant. U the variable, a constant. Now, what these are based on are some well-known Pythagorean identities, right? The objective with trigonometric substitution is to eliminate the radical. That's what we're trying to get rid of, because this is hard enough in here, but we want to get rid of the radical. You do this by using Pythagorean identities. Now, what does this look like? Especially with this being the constant. You can imagine that's like a cosine squared, because cosine squared is 1 minus sine squared. Okay, so if you let u equal sine theta, that would be that substitution. Now, you got to do something with the a. Usually it's a 1 over a, sine times the sine of theta. We'll get to that later, okay? And from this well-known Pythagorean identity that secant squared is 1 plus tangent squared, hey, if you let u equal a tangent theta, then this will be very close to, and you probably need a 1 over a in front or something like that. Oh, no, I said it wrong. Make this a sine theta. Make this a tangent theta. Because then you'll have, if u is a tangent theta, when you square u, you get a squared, tangent squared, then you can factor out the a squared, square root of a squared, a. So that comes on the outside. Same thing down here. Tangent squared theta is secant squared theta minus 1. Here's your trig function, squared minus a squared. So let u equal a times secant theta. And then when you square this, you get a squared secant squared theta minus a squared. Pull out the a. Just have a on the outside, because the square root of a squared is a. And then you have a secant squared theta minus 1 here, which is a tangent squared theta, which you can pull out from under the radical. Hey, not bad, okay? So that's where the trig substitutions come into play. The objective with trigonometric substitutions, eliminate the radical and using these substitutions. So these are going to be our substitutions. Usually they're going to be a sine theta, a tangent theta, or a secant theta, depending on which one of those you have. A sine theta, a tangent theta, and a secant theta. I worked on the farm this weekend, and I have my knee so sore. It hurts to do anything with it, especially get up and get down. But actually, it hurts worse sitting down than it does getting up. But I figure I need to move it to keep it as loose as possible. So, for example, if a is greater than 0, good thing for it to be, let u equal a sine theta, where now, here's the other issue. You need to keep the theta between negative pi halves and pi halves for your sine. The reason for that, anything outside there, it starts repeating itself, and that gets to be problematic. It's not 1-to-1. If within these boundaries, it is 1-to-1. Okay? So then, the square root of a squared minus u squared, if u is a sine theta, then this will be a squared minus a squared sine squared theta. Factor out the a squared, and you have a squared times 1 minus sine squared theta. The a squared can come outside as an a. This becomes a cosine squared. It comes outside as a cosine. You have a cosine theta. This radical here becomes a non-radical here, which you can integrate pretty easily. Now, cosine theta is greater than or equal to 0 because anywhere from minus pi halves to pi halves, it's always positive, okay? Which is a very good thing. Well, still okay. All right. Now, that's going to be the pattern we use in every one of these, okay? So here's your trig substitution. Here's the other thing we're going to do with our trig substitutions. And there is a ulterior reason for doing this. It will make life so much easier on the back end of these problems. Because remember with U substitutions, you always have to go back in and then plug, especially for an indefinite integral, you have to go in and plug back in that. Can you imagine going back and plugging in an a sine theta back in for whatever answer you get? Then you have, it's a mess. I mean, it's doable, but it's just messy. Here's how you can avoid some of the messiness. Draw your little triangles. As soon as you do something like this, and we're always going to assume that a is greater than 0, okay? For intervals involving a squared minus u squared, this is going to be our substitution. Let u equal a sine theta. Now, I like to take that and say, then sine theta is equal to u over a, right? Okay? If sine theta is u over a, I can draw me a little triangle, okay? I will always make it an acute triangle because I like acute triangles. No, okay. Make this my angle theta, and then u over a is opposite over hypotenuse. Hey, what would that make the adjacent side? The square root of a squared minus u squared, which is exactly what that is. Isn't that fun? Okay? But as long as you're between minus pi halves and pi halves, your theta. And I'm not going to mess with any minus pi halves. I'll draw this one, and we'll hook that, and it will be good enough. Okay? If it's a squared plus square root of a squared plus u squared, what is your trig substitution? Help me. Tangent. Let u equal a tangent theta. There it is. As soon as you write that down, then say, then tangent theta is u over a. We'll draw you a little triangle. Any old right triangle. It doesn't have to be this pretty little one. Any one will do. And there's your theta. And your tangent theta is u over a. That's opposite over adjacent. U over a. What does that make this side? The square root of a squared plus u squared, which is exactly what that is. So you see, looking at this is going to help you later. Right now, it seems like it's just something else to do. It will help you later, I promise you. Okay. And for integrals involving u squared minus a squared, what will you use? Let u equal a secant theta, right there. And then do secant theta is equal u over a. Well, secant is 1 over cosine, so that would be hypotenuse over adjacent. Hypotenuse over adjacent. And what does that leave that side to be? The square root of u squared minus a squared, which is exactly that. Okay. Now, this one has a little bit of other issue here because, remember, secant theta is that weird looking graph, and this thing right here could be a tangent theta, or it could be minus a tangent theta, depending on which domain you're in. And I like to always stay in this domain if possible, but occasionally you might wind up down here, so you have to turn things around. Okay. I don't think any of our problems wind up there, but if they do, hopefully something will alert you to that and you make sure you got it right. Okay. And yeah, I think you said all that. So remember what the substitution needs to be, and then draw your little triangle. Those are two things to keep in mind, and basically they're pretty easy from there on. They say, okay. What do you think you were going to do here? Tell me. Anybody? Well, I'll give you a hint. Probably going to involve a trig substitution. What trig substitution does that look like it'll involve?
The first one,
A sine theta. What's your A in this case?
3.
3 sine theta. I like to use a smaller. Let u equal, oh no, let x equal 3 sine theta. Now I like to use theta just because the Greek alphabet, that makes me think, this is an angle we're dealing with, folks, and that's exactly what we are. Now, at this point, I start drawing my little triangle, okay? I always make the triangles look very close to each other. This will be my theta. And what will be what?
3 is the hypotenuse.
Yeah, because sine theta is equal to x over 3. So 3 is the hypotenuse. X is the opposite side. It looks like a y there, but yeah, don't worry about that. X will be the opposite side. What does that make the adjacent side? Square root of? Which is 9 minus x squared, which is exactly what we got in there. Okay. Now, we've started this thing. Let's continue it. On these substitutions, you got 2 tracks to follow. One is where this substitution takes you up here, and the other is where the derivative takes you, the du. And I'm not keeping up with time. I see Dawson is, so let me, okay. So we go till what? 11:40, right? So we've got a good 15, 20, 25 minutes or more, don't we? We're in good shape. Okay. All right. So I really don't care which way we go. I would tend to do this way. This is going to imply that x squared is equal to what? 9. Continue. Sine squared theta. Okay. And this will, I'm drawing out in gory detail now. Next will be 9 minus x squared would be 9 minus 9 sine squared theta. I mean sine squared theta. Yeah, I was right the first time. That's ugly, isn't it? This is really ugly. Quit doing that. Oh, I can't get that. Oh, it finally erased. Okay, now that'll erase. Okay. Sine squared theta. Okay. Now, the next thing we want is the square root of 9 minus x squared. So I'll put a square root here and the square root here. And this would be, factor out the 9, and what do you get? You want to do it inside, radical outside? I don't care. Let's do it inside. Square root of, factor out the 9, and what does that leave you with? It's not 1 minus sine squared theta. And what's 1 minus sine squared theta? Okay, so this is square root of 9, which is 3, and the square root of cosine squared is cosine theta. Okay. Now, let's go down this route. Okay. Then, dx, we need that also, is what? Not that hard. Help me, somebody. Please. I'm drowning. X is 3 sine theta. What is dx? Three cosine theta. One more little thing. D theta. D theta, right? Chain rule. All right. We've got all our pieces in place, right? So let's rewrite the integral. This one up here becomes this integral here. The dx is 3 cosine theta d theta, right? The x squared is 9 sine squared theta, right? See from there? And the square root of 9 minus x squared is 3 cosine theta. Well, guess what, team? The 3 cosine thetas cancel out, and what we're left with is a big boo hiss. The integral, I'm going to pull out the 1/9 here, and that would be d theta over sine squared theta. Now, why in the world did they give you like this one for your very first example here? But they did. All right? Now, I know it was last week, and that was a long, long time ago that we did how we managed sine squareds. Anyone remember? Make sure I'm not chasing down a rabbit hole here. Yeah.
Change it to cosecant squared.
Okay, that's exactly what the book does. You could have done it a different way, but the book does it this way. It's 1/9.
What's the other way?
Okay. That is a remember a half angle, double angle type thing, you could go that route. This way is the easier one. Okay, this will be the integral of cosecant squared theta d theta. Now, does that ring a bell? Think of the ones we usually use.
That's negative cotangent.
Negative cotangent. Remember, tangent, derivative of tangent is secant squared, so the derivative of cotangent would be a minus cosecant squared. Okay, so that gives you minus cotangent theta plus c. But we didn't start out with thetas. We don't want to wind up with thetas. So how are we going to get that to be back to x's? And this is what I was talking. Oh my goodness, the 10 o'clock scholar. Okay. Ryan's here. We're just missing Tiara. And if I'm not mistaken, she had emailed me that she was sick. I just saw the title. I didn't get a chance to open it, so I'm sorry that she's sick. Okay. Now, what you could do, if you're really messy about it, is try to go up here and figure out that if x is equal to this, then x over 3 would be the inverse sine of, don't do that, please. Go to your triangle. And what is the cotangent of theta? What is cotangent?
Cosine over sine.
Second? It's cosine over sine, but in terms of your right triangles. Adjacent over opposite. You're absolutely right. So this will be minus 1/9. The adjacent side is the square root of 9 minus x squared over x plus c. That's it. Thank you, triangle, for saving us having to go through and make up and try to devise some way to do a cotangent of an inverse sine. Oh, I didn't want to do that. This way, it's done for you. See how handy those little triangles are. Okay? Let's see how the book did it. Minus, they put the 9x in the denominator, that's fine. A minus the square root of 9 minus x squared over 9x plus c. Yes. Good deal. And you see, it seems a bit much to write out all the steps, but actually sometimes having all those steps in there, you'll see where you can go back. And having the x squared here gave you something to plug in here. Having you the square root of this to be that gave you something to plug in here. And then all of a sudden things start dividing out and stuff like this, and you wind up in a pretty good way to go. Okay? And then your little triangle really helps when you have messy things like this at the end. Look at the triangle. That's the theta. Figure out what the cotangent of theta is. Opposite. Adjacent over opposite. And it's done for you. Okay? So, that's how we did it. Let's see if they did it. Any other steps, links, techniques, or other things. First note, the basic integration rules do not apply, okay? Now, if you had an x dx in the numerator, you might have some grounds to try a substitution. But that's not an x dx, that's just a dx. So yeah, you can't use substitution and nothing else, except maybe a table, and whether you can find that in the table, I'm not sure. I'm sure if your table was big enough, you might. Okay? But use the trig identity. Observe that 9 minus x squared is in the form of a squared minus u squared. where u is x and a is 3. So you would have x equal a sine theta, which is 3 sine theta. Okay? There's your trig substitution. All right? Now, whether they go to as much, yeah, they do a lot of it. Okay? They don't do it in a very orderly fashion. They just say, behold, this is it. But if you take it a step at a time, x equal, I don't have it written anywhere here, it's on the previous slide, x equal 3 sine theta, okay? Then on the one hand, sine theta is this, that gives you your triangle, opposite over hypotenuse. Got it? And that leaves this side being your 9 minus x squared. Okay? But also, x equal 3 sine theta, since you are going to need an x squared, both there and in the original problem, go on and square that x. The x squared equals 9 sine squared theta. That would be my next step, not this one. And then 9 minus this, factor out a 9, 1 minus sine squared theta would be a cosine squared theta. So the square root of 9 is 3, the square root of cosine squared is cosine. So that gives you that. Then at the same time, do your dx, because you're going to need that as well. And if x is equal to 3 sine theta, then dx is equal to 3 cosine theta d theta. And then you put all this back together under your in the integral, okay? And your dx goes here. Your x squared from there goes here. And your 9 minus x squared goes here. Okay? Square root of 9 minus x squared. And these completely go out, and that leaves you, I think they just jumped right to, no they didn't. They did a 1/9 on the outside, very good. Integral of d theta, that's all that's left up here, over sine squared theta. And then, as Patrick noted, that is cosecant squared theta. Okay? And that's a perfect antiderivative, or derivative of minus cotangent. Okay? So that becomes minus 1/9 cotangent theta plus c. Okay? And that would be your answer if you were dealing with thetas. You weren't dealing with thetas. Your original problem had x's in it. There's where the triangle comes into play again and enables you to do what is cotangent of theta. Well, cotangent of theta is adjacent over opposite. So that would be minus 1/9 square root of 9 minus x squared over x plus c. And they took one more step to make it minus the square root of 9 minus x squared over 9x plus c. Either one of those answers would have been fine. You don't have to write it the way they do, unless you're doing WebAssign. And by the way, I need to get you all the WebAssign codes. I've got to get my grades in for first mini-term. I've also got to get my student learning outcomes in that were due Friday, and I was so busy trying to get an instructor for 2 classes that I didn't have time to finish those either. Second mini-term classes. And I've still got that to do, both of those things to do. And at some point I need to be working on another big project that we've got. But sometime in between, I'll try to get your codes to you as soon as I can. Okay. Note that the triangle in figure 8.6 can be used to convert the thetas back to x's. That's exactly what we did. Not only is it helpful in one sense there, this is where it's really helpful. And that gave you that. In fact, I don't know how they got it other than that. So this is a bit anticlimactic. It should have been written before that. Okay. Now, trigonometric substitution can be used to find the 3 integrals listed in the next theorem as well. Those integrals will be encountered several times. This is just a direct thing of u is equal to a sine theta. U is equal to, what's this one? The second one. Yep. What's your trig substitution for that? What's the trig substitution there? Number 2.
Secant theta.
You secant theta, and this one would be third one.
Tangent theta.
You tangent theta, exactly. Now, they write these out, which are perfectly fine. Am I going to sit down and remember those? No, it's so much easier to do them. Yes.
Going to that, it skips example 2, 3.
Did we skip some examples? Oh, did we ever? Glad you caught that. I was looking at the slides rather than at the book. Sorry. Before we get to woo, yes, we got example 2, 3, and 4 to do. So let's go back. We'll get back to that later. Good catch there. Okay. Any questions on example 1? I guess I'd already asked that. Okay. Now they did have a little thing at the bottom of page 542 is a technology deal there. And basically it gives 3 different things there. Use a computer algebra system. Since I don't have one, I'm not going to really mess with it. But the same procedure works for all 4 of those integrals as what we just did. Okay? And then they start talking about inverse hyperbolic functions, and I really have very little need for those. I hope if you do have a need for them, you can go back and recreate this, but I remember doing them and never using them until we did them again, and then never using them until you did them again. So take a look at those if you're interested. Let's do example 2. These are things you will be seeing again. Let's do this one. The integral of dx over the square root of 4x squared plus 1. Okay, this is in many senses it's a subtle different, but a very different kind of an approach to this. What do you reckon your substitution is going to be? Say again? Tangent theta. And what will it be? Now, okay, let's try that. Let what then be tangent theta? Say again? Okay, I hear one. I can't make out what I'm hearing. No. Okay. We want to do a trig substitution that's going to help us get rid of that radical. So let's not include the radical in it. Any idea what it'll be? Would it help if we did sort of an intermediate little substitution? Okay? I'll just do it here. Let u equal 2x. Would that be helpful? Then let's take this down. Then du is equal to what? Dx. Okay. And because you don't have a 2dx, let's make dx equal du over 2. All right there? Now, what does this look like? This looks like the integral of 1/2, there's your over 2, du over the square root of
U squared plus 1.
yes, u squared would be 4x squared. U squared plus 1. Now that, if that's helpful to you, you can do your trig substitution there. Let u equal, what were you saying? Tangent theta. Now, you could have started out with let 2x equal tangent theta. That's what I was trying to get at, and I thought, well, maybe doing one u substitution first will make that seem more obvious. Okay? So you okay with that now? Then du is equal to what? Help me. I don't. I believe that's right. Secant squared theta. One more little thing. You may have said it. D theta. Okay. Now, let's pursue this way what u squared is. What would that be? Pretty simple. Tangent squared theta. Okay. Now let's pursue a little bit further and do a u squared plus 1. Would be tangent squared theta plus 1. And then let's do a square root of that, because that's what we have, and a square root of this. And what would that be? What is tangent squared theta plus 1? Secant squared theta is secant squared theta, right? And the square root of secant squared theta is secant theta. All right. Now, let's also, don't forget our handy-dandy little triangles. So let's draw a little triangle here. Now, I'm all in favor of going back, and let's just assume that's the right angle there. And this is our angle theta. That's just how I like to draw them. Okay. Let's go back to and sort of combine these two things together. U, which is 2x, equal tangent theta. So let's do tangent theta equal 2x. And I'll put that over 1 if that's okay. Is that all right with you?
What does that say?
Tangent theta from here is equal to u, but u is equal to 2x. So tangent theta is equal to 2x. But I put over 1 in it. Is that all right to do? Legal in most states, right? All right. So what would then be our theta? If that's the theta, what does that represent? Tangent theta is opposite over adjacent. So that would be 2x over 1, right? And then what would be our hypotenuse be? The square root of 4x squared plus 1. Ding, ding, ding. That's what we started with, isn't it? Okay? We don't really need that now, but there it is for when if we need it in the future, we'll have it. All right, so let's start and let's do our u's here. This is 1/2 the integral. What was our du? Secant squared theta d theta. So that's in our numerator here. And what was our square root of u squared plus 1? Secant theta. Okay. Well, this secant theta will go into one of those, leaving you just the integral of secant theta. Now, does anyone happen to remember what that is? antiderivative of secant theta. That's that weird one, remember?
Secant theta plus tangent.
Say again.
Secant theta plus tangent.
It has to do with that, but it's the log of that.
Oh.
Yeah, okay. 1/2 the log of absolute value secant theta plus tangent theta. And then what?
Plus C.
Plus C. Okay. But this has thetas in it. Our original problem did not. And that's where I like to go back to our handy-dandy triangle. Okay? This will be 1/2 the log of, in fact, we could if we wanted to, let's not yet. We'll see if we want to do it later. Square root of, absolute value of, and what is secant theta? Which is? That's cosine. Yeah, that is adjacent over hypotenuse. So secant would be hypotenuse over adjacent, right? So this will be absolute value of the square root of 4x squared plus 1 over 1. Okay. Now, that's fine. And then plus, and what's tangent theta?
2x over 1.
2x over 1. So that'd be 2x. Okay. Plus c. Now, I'm perfectly happy with that answer, okay? And we didn't start out with any knowledge of what x is, so since x could be negative, we might need to leave the absolute value bars up there. Let's see. That's how they leave it, isn't it? Good for them. One of the rules of logarithms tells you you can take the coefficient of the logarithm and make it the exponent here. So you can make it the log of this thing, absolute value of this thing to the 1/2 power. But they didn't, so I'm happy to leave it just like that. All right, good deal. Any questions on that? Do you see how we came up with such a bizarre little answer like that? And it says, try checking this result with a computer algebra system. Is the result given in this form or in the form of an inverse hyperbolic function? That would be another reason for not using a computer algebra system in my mind. Okay, this is perfectly fine for me. Okay. Now, next little statement here, you can extend the use of trigonometric substitution to cover integrals involving expressions such as a squared minus u squared to the any kind of power n over 2, okay? In other words, square root of something to a higher power. And they give the substitution. It's a pretty direct substitution, so I think we're going to do it on the next one. So let's clear the screen and do example 3. Do we have time?
4 minutes.
Yes, 4 minutes. I'm guessing not. Are y'all guessing that too? I bet you are, okay? So we'll start off with example 3 next time, which means I need to wipe out my arrow there. Okay, let me get my papers in place here. And homework exercises in this section will include either 3 or 5. They both should be at Calc Chat. And either 11 or 13, they should both be, 7 or 9. They should both be at Calc Chat. 7's at Calc View. I think you can do 11 or 13. I think we did something close enough to those. You should be able to do them. They're at Calc Chat also. The special integration formula is there. I think you can probably do those. Give them a shot anyway. They should both be at Calc Chat. And 19 to 21, ooh. Let's stop there. We'll pick up the rest of those next time. Okay? So just stop at 17, perhaps. Because you got plenty to do in the other section, too. All right. And again, since some people came in after I said this, and maybe some of them have left, too, so sorry about that. I do need some scores in this class before Wednesday. Either research papers or test ones. I've only received 2 test ones. Yes.
Just to make sure again, so we can
Say this again.
turn it in Wednesday morning, and that's fine.
That'll be fine. Yeah. I'll do my report in the afternoon or sometime. If I don't do it till Thursday, they can slap my wrist, but it'll all be the same. Okay. Yes.
And you said if we don't, all they're going to do is just start, you can put a 0 in the midterm for the month.
Okay, say this again.
If you don't turn it in by today, you just get a 0 in the midterm. And
No, they just ask they ask us to report any students who have a D or an F at midterm. I'd have to report that you had an F at midterm. It's not going to matter to anything. It doesn't affect grade point. It doesn't do anything. It just may have people contact you and say, hey, do you need tutoring? And if you do, then that's advantageous. If that just becomes a pain for you, to have to deal with answering emails or whatever, or coming to see people, then get me something so you don't have to go through that. That's all it is. Not going to change your grade at the end. It's just going to see anyone who legitimately is struggling at midterm. It gives them a chance to struggle a little less, maybe.
how many tests are we having this semester?
Probably 3. Okay.
We had four last guys.
Yeah, I know, but those were shorter chapters than these.
You about right.
We had that one on chapter 7, the one on chapter 8, and then chapter 9, we only do a couple of sections in it, if I'm not mistaken. This is a long, long section.
They've all been long sections.
Yeah, it's long chapter. Okay, that's why 9 we'll only do sequences 9.1 and series 9.2. Then we go to chapter 10, which I think we do we don't do 10.1. We do 10.2, plane curves and parametric equations, 10.3, which is parametric equations and calculus, and I think 10.4, polar coordinates and polar graphics.
Will 10 be our final?
That will be I think so. I think that will be the end. If we have a chance, I'll do as much as we can in 11. If we get very far in 11, we may have 4 tests. But at this pace, I don't think we will. I think it'll just be finishing 8, doing 9, 10, and whatever we can do in 11. Those will be 1 test.
I've asked around for tutoring, so I'll probably just take that up.
Okay. All righty. Yeah. It's not a bad thing, but just if you found it annoying, then go on and get me in something. If you want it documented, that'll be fine too. Yeah. Okay.